So today we are going to discuss the very important effect in metals and semiconductors, that is namely Hall effect. So basically in this experiment, the Hall effect will be used to study some of the physics of charge transport in metal semiconductor samples. In 1879, E. H. Hall observed that when an electrical current passes through a sample placed in a magnetic field, a potential proportional to the current and to the magnetic field is developed across the material in a direction perpendicular to both the current and to the magnetic field. This is the current, this is the magnetic field, so your VH will be developed. This effect is known as the Hall effect and is the basis of many practical applications and devices such as magnetic field measurements and position and motion detectors. With the measurements he made, Hall was able to determine for the first time the sign of charge carriers in a conductor, right? So even today, Hall effect measurements continue to be a useful technique for characterizing the electrical transport properties of metals and semiconductors. Indeed, the failure of the simple model of metallic conductivity, which we discuss now, to account for many experimental measurements of the Hall effect has been one of the principal motivators leading to a better understanding of electronic properties of materials. So, in order to understand some of the ideas involved in theory of Hall effect is in real materials, it is instructive to construct a more careful model for electric currents under electric and magnetic fields from a classical point of view, right? So we imagine that the charge carriers move in a medium that offers some resistance. The resistance is due to scattering between the carriers and impurities in the material and between the carriers and the vibration of the material's atom. So each charge carrier is accelerated by the applied fields, but every so often it scatters and loses energy. So in a way, Hall tried to determine whether the force experienced by a current carrying wire in a magnetic field was exerted on the whole wire or only upon the moving electrons in the wire. So he suspected it was the latter, and his experiment was based on the argument that if the current of electricity in a fixed conductor is itself attracted by a magnet, the current should be drawn to one side of the wire, and therefore the resistance experienced should be increased. So his efforts to detect this extra resistance was unsuccessful. But Hall did not regard these as conclusive. The magnet may tend to deflect the current without being able to do so. So it is evident that in this case, there would exist a state of stress in the conductor, the electricity pressing as it were toward one side of the wire. This state of stress should appear as a transverse voltage known today as the Hall voltage, which Hall was able to observe. Hall's experiment, an electric field Ex is applied to the wire extending in the x direction and the current density Jx flows in the wire. In addition, the magnetic field, let me discuss this. Okay, look at this. An electric field Ex is applied to a wire extending in the x direction and the current density Jx flows in the wire. In addition, a magnetic field points up in the positive z direction, H. As a result of the Lorentz force, When dealing with non-magnetic or weakly magnetic materials, we shall always call the field H the difference between B and H being extremely small. Remember this. So what I'm saying, that the Lorentz force, that is minus E by C V cross H, right? Minus E by C V cross H, that is the Lorentz force, acts to deflect electrons in the negative y direction, right? Negative y direction. That is, an electron's drift velocity is opposite to the current flow. If this is the current flow, this is always opposite to that. Uh, so however, the electrons cannot move far, very far in the y direction before running up against the sides of the wire. As they accumulate, there an electric field builds up in the y direction and opposes their motion, and then further accumulation. So in equilibrium, this transverse field or the Hall field EY will balance the Lorentz force, and current will flow only in the x direction. This is the basic directional indications, and this is the schematic view of the Hall's experiment. So imagine your left hand side, left hand rule, and your three fingers from the mid finger to the uh, big finger. If you place the electric field, the Hall, sorry, the magnetic field and the direction of the uh, electronic, the direction of the y direction of the electric field, you got the right direction. So there are two quantities of interest. One is the ratio of the field along the wire Ex to the current density Jx, which we eventually called, this is magnetoresistance. More precisely, it is the transverse magnetoresistance. There is also a longitudinal magnetoresistance measured with the magnetic field parallel to the current. So which Hall found to be the field dependent. The other is the size of the transverse field EY. Since it balances the Lorentz force, one might expect it to be proportional both to the applied field H and to the current along the wire Jx. So one therefore defines a quantity known as the Hall coefficient, which is RH is equals to EY times JXH. Note that since the Hall field is in the negative y direction, this direction, RH should be negative. If on the other hand the charge carriers were positive, then the sign of their x velocity would be reversed, and the Lorentz force would therefore be unchanged. As a consequence of the Hall field would be opposite to the direction it was for the negatively charged carriers. So in a sense, it means that a measurement of the Hall field determines the sign of the charge carriers. Hall's original data agreed with the sign of the electronic charge later determined by Thomson. So one of the remarkable aspects of the Hall effect, however, is that in some metals the Hall coefficient is positive, suggesting that the carriers have a charge opposite to that of the electron. Uh, so to calculate the Hall coefficient, this one RH equals to 1 upon NEC, and magnetoresistance, we first find the current density vectors Jx and Jy in the presence of an electric field with arbitrary component Ex and Ey, and in the presence of the magnetic field H along the z-axis. The force acting on each electron is F equals to this one. F is equals to minus E times electric field plus V cross H upon C, and therefore for the momentum per electron becomes dp dt is equals to minus E times E plus P upon mc cross H minus P upon tau. So in the steady state, the current is independent of time, and therefore Px and Py will satisfy this equation, that is dp dt is equals to 0. This turns out to be minus Eex plus omega c Py minus Px upon tau, and likewise the same equation for Ey, where omega c is the cyclotron frequency, that is Eh upon mc, and multiply both these equations by any tau upon m and introduce the current density component to find if sigma naught Ex equals to omega c tau jy plus jx, and sigma naught Ey is equals to minus omega c tau jx plus jy, where sigma naught is simply the Drude model DC conductivity in absence of the magnetic field. So the Hall field Ey is basically determined by the requirement that there be no transverse current Jy. Setting Jy to 0 in the second equation of this, Ey is simply minus omega c tau upon sigma naught jx, that is minus h upon nec jx, and therefore the Hall coefficient, which is the functional value of Ey by jxh, is simply 1 upon minus 1 upon nec. So this is very striking result, for it asserts that the Hall coefficient depends on no parameters of the metal except the density of the carriers, this n, right? Since we have already calculated n, assuming that the atomic valence electrons become the metallic conduction electrons, a measurement of the Hall constant provides a direct test of the validity of this assumption. So what happens basically in case of Hall effect is the experimental evidence leading us to introduce the concept of positive current carriers or holes in crystals is furnished by the Hall effect. So when a conductor is placed in a magnetic field like this, perpendicular to the direction, this is the direction of the magnetic field, and perpendicular to the direction of the current flow, a voltage is developed across the specimen in the direction perpendicular to both the current and the magnetic field, as shown in this figure. So this figure suggests that the electrons flowing in the x direction in the presence of the magnetic field Hz are deflected towards the lower face of the specimen, which then changes up until the resulting electric field cancels the effect of the magnetic field. So the voltage, this voltage is called the Hall voltage, and it is developed because the moving charges making up the current are forced to one side by the magnetic field. The charges accumulate on the face of the specimen until the electric field associated with the accumulated charge is large enough to cancel the force exerted by the magnetic field. The Hall effect is an important tool, especially in semiconductor research, as in simple situations, the effect provides a direct estimate of the concentration of the charge carriers. We can easily calculate the concentration of the charge carriers by simple Hall effect measurement. So it is usually assumed in calculating the Hall voltage that the specimen is in the form of a thin plane slab and the voltage is developed across the narrow dimension as shown in this figure. So the Lorentz force on a charge carrier is force is equals to E times electric field plus 1 upon C V cross H, and the Hall electric field in the y direction is given by the condition Fy is equals to 0 equals to E times Ey minus 1 upon C Vx Hz. And for the geometry as shown in the figure, thus Ey is equals to Vx Hz upon C, that is Jx Hz upon NEC, where Jx is the current density and capital N is the carrier concentration. So the ratio RH is simply Ey by Jx Hz, that is 1 upon NEC, is called the Hall constant and is negative for free electron. The value of the Hall coefficient in electrostatic units is stat volt centimeter or stat ampere or state, is the magnitude of 10 to the power minus 24 for normal metals. It will be much larger in semiconductors as N is smaller. So the value of the Hall coefficient in practical units, volt, centimeter or ampere or state, is roughly 9 into 10 to the power 11 times the value in electrostatic units. So it is often convenient to consider the Hall angle, that is phi, is defined as Ey upon Ex, and which is simply this sigma hz upon NEC, and this is E tau h upon m star c, that is mu h upon c. EH upon MC, EH upon m star c is just the cyclotron angular frequency omega c for a free particle of mass m star in a magnetic field H. Thus phi is simply omega c tau, right? Where tau is the relaxation time. Simply phi is equals to omega c tau. Tau is the relaxation time. The Hall angle phi is equal to the average number of radians, usually fractional, traversed by a particle between collisions. All results discussed assume implicitly the energy band is of the simple form Ek is equals to h cut square k square divided by 2 m star. The simple result Rh equals to 1 upon NEC can be shown by more rigorous methods to apply to a Fermi-Dirac distribution of identical carriers. The numerical factor is altered slightly for a Maxwellian distribution. The expression becomes somewhat more complicated if both electrons and holes contribute to the conductivity, and the solution is considered in any kind of p-type or n-type semiconductors, where both majority and minority carriers are involved in charge transport. For the monovalent metals, the calculated concentration of valence electrons are perfectly matches with the experimental values and gives the quite satisfactory results. However, the sign of the effect in beryllium, zinc and cadmium is opposite, so that the predicted for electrons. A positive, so a conclusion is that this one. So the conclusion is that this a positive Hall constant implies that the current is carried by positive charges. So we can furthermore see that on band theory, vacant states near the top of an otherwise filled energy band behave as if endowed with a positive charge. States of this character give rise to the positive Hall constants. The anomalous large value of the constant for Bismuth is interpreted on band theory as given by a low concentration of electrons outside nearly filled bands. In order to understand some of the ideas involved in theory of the Hall effect in real materials, it is instructive to construct a more careful model for electric currents under electric and magnetic fields from a classical point of view. We imagine that the charge carriers move in a medium that offers some resistance. The resistance is due to scattering between the carriers and impurities in the material, and between the carriers and vibrations of the material's atoms. Each charge carrier is accelerated by the applied fields, but every so often it scatters and loses energy. If we assume that the average time between the scattering events is tau, then we have on average a retarding force acting on the carriers is F retard is equals to minus mv upon tau, where m is the mass of the carrier. So under the influence of applied electric and magnetic fields, Newton's second law reads m dvdt is equals to q times E plus v cross b minus mv upon tau, where the velocity v is taken to be an average over all the carriers. At steady state, the time derivative of b will vanish. Under the usual convention that b points along the z-axis, we obtain the component equations for b by setting the left side of equation this to 0 and rearranging vx, we get this, vy we get this, vz equals to this. And we already know that jx is equals to nqvx and correspondingly y and z components. By solving the equations for vx, vy and vz in terms of the component e vector and vz, we get jx equals to this, jy equals to this and jz equals to this, where we assumed sigma is equals to nq square tau by m and omega c is equals to q bz by m. In the expression for the conductivity sigma, it may seem that all we have done is to replace one unknown quantity v with another equation tau, but the parameter tau is called the relaxation time, and the angular frequency omega c is known as the cyclotron frequency. It is the frequency of rotation of a charge in a magnetic field and can be taken as a measure of the strength of the field. The combination omega c tau is used to characterize an experimental situation if the magnetic field is weak or the relaxation time is short, that omega c tau is far lesser than 1, and our experiment is in the weak field limit. Alternately, if omega c tau is far greater than 1, the experiment is in the strong field limit. A number of materials show different behavior between the weak and strong field limits. Aluminium is one. So in our classical model of the Hall effect, with a single type of charge carrier, however, there is no such crossover between the weak and strong field. This can be proved by working out different examples of cyclotron frequency and magnetic field P. So the classical theory of the Hall effect presented before assumes that the electric current is the result of many charge carriers moving independently of each other and responding to applied fields as classical particles. But we know that electrons are quantum particles, specifically fermions, and they have wave-like properties, right? So curiously, the act of changing the model from classical independent particles moving freely to quantum independent particles moving freely changes little in the results so far presented, and the free electron quantum gas model still predicts a Hall coefficient of 1 upon nq and zero magnetoresistance. The benefit of using quantum approach becomes apparent when it is coupled with a more realistic model of solid matter, specifically crystalline. In a crystal, the atoms are arranged in a periodic lattice. Electrons in the lattice feel the effect of a periodic potential on their motion. The strongest effect occurs for those electrons in the outer atomic orbitals or the valence electrons, and especially those valence electrons whose de Broglie wavelength is close to the spacing of the potential's periodicity. Within the periodic potential, the allowed energies of the valence electrons are broken into a series of energy bands with energy gaps between them. If the number of valence electrons per unit cell of the crystal is exactly enough to fill a band, the solid will be a poor conductor, since by symmetry at each energy there will be field momentum states pointing in opposite directions. Conduction can only occur if an electron can jump a gap into an unoccupied state. If the gaps are large, the necessary energy may be too high and the solid is an insulator. If the gap is small, then the thermal energy may be enough to cause sufficient electrons to jump the gap, and the solid is called a semiconductor. On the other hand, if the number of valence electrons per unit cell is not enough to fill a band, then many unfilled momentum states lie within easy energy reach. And solid is a good conductor, that is a metal. However, the shape of the energy surfaces, the band structure has a strong effect on the type of conduction that can occur. Electron states with energies near the bottom of a band, the lowest allowed energy in the band, behave like free electrons, except that their response to an applied field may be that of a behavior of lighter particles. It as if the electron mass m has been changed to an effective mass m star. While this statement seems a little strange, because the electrons with energies near the top of a band, these electrons can act as their mass is negative. In other words, they accelerate oppositely a free electron when acted upon by a applied field. Indeed, it is easier to imagine particle states of this type as acting like positive charges. Such states are called hole states. So in a semiconductor, the band gap is relatively small and electrons may be excited by thermal energy to jump the gap. This process allows an electron-like state near the bottom of an upper band and a hole-like state near the top of a lower band to come into existence. Both states carry current, with the whole state acting as a positive charge. The number of these current carrying states depends on the temperature in a roughly exponential way. The number is proportional to the Boltzmann factor, that is e to the power minus Eg upon kT, where Eg is the energy of the gap or the band gap energy. The idea of simultaneous electron plus hole states has yielded a useful model of the Hall effect called the two-band model. The mathematics works rough through, except that the total current is the sum of contributions from the holes and the electrons. If we let each type of the carrier have a Hall coefficient Re for electrons and Rh for holes, and we assume that the conductivity sigma is the electronic conductivity plus the hole conductivity, then we can derive an expression for the total Hall coefficient as Rh equals to sigma h square Rh plus sigma e square Re divided by sigma h plus sigma e whole thing square. So in this, the effective mass m star is substituted for m and the charge q taken as positive for holes and negative for electrons. So this equation, in the limit omega c tau is far lesser than 1, the low field limit. I have already discussed about the low field and the high field limit in these equations. So in the case of semiconductors, it has become customary to separate out the carrier density n from the overall conductivity formula sigma and define a new quantity called the mobility as modulus of q tau by m star. Thus, in our two-band model, the conductivity would look like sigma equals to any tau, or the mu, any mu, sigma is equals to any mu, that is mu e times the modulus of QE. Either this should be hole or this should be electron. So we get the modulus. So the total conductivity would look like sigma equals to electronic carrier density times the charge times the mobility of electrons. Same likewise, the mobility of hole, the charge of the hole, and the carrier density of the hole. And the low field Hall coefficient would look like RH equals to 1 upon modulus of Q and NH mu H square minus NE mu E square divided by NH mu H plus NE mu E whole thing square. This comes from this formula, right? We have substituted the value of mu H in sigma H and sigma E. So finally, we come across this Hall coefficient for the two-band model, or in the semiconductor where both minority and majority carriers are present, would look like this instead of 1 upon NEC. So where we have assumed that the charge is the same magnitude for both type of carriers, that is for hole and for electrons. So I have given two exercises for the students. If you are interested, you can solve this and communicate with me. This is the very fundamental about the Hall effect and Hall coefficient, I would say.